Hello students, in previous video we have studied about principle of superposition of waves. Now after that we are going to study about a phenomena known as interference of light, which is actually based on the principle of superposition of waves only. It is a result of superposition of two or more waves. So to understand interference of light, we have to assume that there are two light waves such that the light waves have same frequency. Other than it, they are traveling in same direction and they have either zero or constant phase difference. So we are considering two waves, two light waves of same frequency. First condition is the waves should be of same frequency. Second condition is the phase difference between them should be either zero, means no phase difference, or either zero or constant phase difference. And these waves should be traveling along the same direction. So they should travel in same direction. If we have such two waves and these waves superpose each other, then the intensity, as a result, what we get, the intensity in the region of superposition get redistributed. Means initially the value of intensity was something else, but after superposition we get a new distribution of intensity in that region of superposition. At some points we get maximum intensity, at some point we get minimum intensity. So this redistribution of energy or this redistribution of intensity in the region of superposition of waves is called interference of light. So when we have two light waves of same frequency, zero or constant phase difference, traveling in same direction, superpose each other, then the intensity in the region of superposition get redistributed Now redistributed means at some point we get maximum, at some other points we get minimum. So this redistribution of energy is called the interference of light. Superposition gets redistributed. This phenomena of redistribution of energy, right? So the phrase we are using is redistribution of energy is called interference of light. This is the phenomena of interference of light, in which energy get redistributed because of the superposition of waves. But the conditions are, necessary conditions are, the waves should be of same frequency, they should travel in same direction, and the phase difference between them is either constant or there is no phase difference or zero phase difference between them. So this phenomena is called interference of light. Now this phenomena was first experimentally demonstrated by Thomas Young, and that's why we call its experiment as Young's double slit experiment. Young's double slit experiment, and in some books you can also see it written as YDSE. So this is Young's double slit experiment, which is actually the experimental demonstration of this phenomena of interference of light. Now Young, in his experiment, he take a source of monochromatic light. He take a source of monochromatic light, and that source illuminates a rectangular narrow slit S. So this is a narrow slit S of about 1 mm wide, and it is illuminated by a monochromatic light source, for example a sodium vapor lamp or some source like that. Now after that there are two parallel slits S1 and S2. These are two narrow parallel slits S1 and S2 which are arranged symmetrically and parallel to the slit S. Means the position of these two slits is symmetrical and parallel to the slit S, and these are at a distance of about 10 centimeter from it. The distance between this source slit and these two slits is about 10 centimeter. The separation between these two slits S1 and S2 is about 2 mm, and the width of each slit is about 0.3 mm. Now after this there is a screen placed here at which the pattern or the redistribution of energy was observed. So this distance capital D, or the distance of that observation screen from the two slits, is about 2 meter, and alternate bright and dark bands appear on the observation screen while doing the experiment, and these alternate bands are called interference fringes. Okay, dark fringe and bright fringe. Dark band is called dark fringe and bright band is called bright fringe, or they commonly known as interference fringes. Now if we close any one of the slit S1 or S2, if we close any one of the slit, then instead of two there is only one wave. Superposition doesn't happen there. So because of that, if we close one slit, either S1 or S2, the appearance of bright and dark fringe stops. There is no bright and dark fringe then, and the intensity of light becomes uniform. This shows that if you have a single source, you get uniform intensity of light on the screen, but when we place slits here, there are two waves superposing at different points on the screen and giving us either bright or dark interference fringes. So this is the phenomena of interference which was experimentally observed by Young's and is known as Young's double slit experiment. So in Young's double slit experiment, the apparatus he used contains a monochromatic source that illuminate the slit S, right? It illuminates the slit S, and the slit S is about 1 mm wide. After that there are two parallel narrow slits, two parallel narrow slits S1 and S2. These are arranged symmetrically and parallel to the slit S. Now the size of these slit S1 and S2 are approximately 0.3 mm wide, and the separation between S1 and S2 is approximately 2 mm. The separation between them is approximately 2 mm, and the size of these narrow slits is about 0.3 mm. Now a screen is placed there. After that there is a screen जहाँ पर हम observation लेंगे. A screen is placed at a distance of approximately 2 meter from these two slits. This is the arrangement that Young's used in his experiment to obtain interference fringes, and he observed pattern of bright and dark fringes on that screen, and we call it as interference fringes. So in Young's double slit experiment, as we see in the arrangement, they used a source, an illuminated slit S, and after that they used two parallel narrow slit S1 and S2. The need of using S1 and S2 is that these two slits S1 and S2 act as two coherent sources. They act as two coherent sources. Now coherent sources are such sources which emit monochromatic light of either no phase difference or of constant phase difference. So the conditions that we need for interference are only fulfilled if we use two coherent sources, because exactly monochromatic, exactly same frequency के two rays obtain करना at the same instant in the same phase without any phase difference is not possible practically. So we use two coherent sources that are made up of a single source S only. So we are using two coherent sources S1 and S2 which are made up of a single source that is illuminating the slit S, so that the rays we are getting, they will be of exactly same frequency and the phase difference between them is either constant or zero. So to maintain that condition necessary for interference, we are using two slits S1 and S2, and because of this, as all the conditions are valid, interference take place between the waves diverging from these sources. The rays that are diverging from S1 and S2, these rays superpose each other and interference can be observed. Now there are certain conditions like when we get maximum brightness and when we get minimum brightness, and these conditions are called condition for constructive interference and condition for destructive interference. So I'm dividing it for two sections. This is for constructive. Constructive interference means we are getting a bright fringe or maximum intensity. Destructive interference means we are getting a dark fringe or minimum intensity of light or energy on at that point. So we are finding condition that when we will get constructive and when we will get destructive interference. So first we are talking about the condition for constructive interference. To find the condition, first we have to find the expression of intensity. Only then we can find then what will be the maximum value of it and at what points we will get its maximum value. So if there are two waves y1 y2, means there are two waves which are displacing or the particles of the medium by the displacement y1 and y2, such that y1 is a1 sine omega t and y2 is a2 sine omega t plus phi. Now phi is the phase difference between the two, and that is a constant. Phi is a constant phase difference between the two waves. Now by the principle of superposition, the resultant wave we get will have the displacement y is equal to y1 plus y2. The resultant displacement will be y is equal to y1 plus y2, and on solving this we get y is equal to a1 sine omega t plus a2 sine omega t plus phi. By using trigonometric relation, it is a1 sine omega t plus a2. Now sine a plus b is sine a cos b, means sine omega t cos phi, plus cos a sine b, means cos omega t sine phi. Again we split this bracket and take sine omega t as common, then we get y is equal to a1 plus a2 cos phi sine omega t plus a2 sine phi cos omega t. So this is the displacement, the resultant displacement at point P that we get because of the two waves. Now we assume that this expression a1 plus a2 cos phi is equal to a cos theta and a2 sin phi is equal to a sin theta. By squaring and adding this equation, we can get a square is equal to a1 square plus a2 square plus 2a1 a2 cos phi. This we get by squaring and adding these two equations. Also if we put these values, then y is equal to हो जाएगा a cos theta sin omega t plus a sin theta cos omega t, or we can write it as y is equal to a sine omega t plus theta, which is the resultant displacement. So here y is the resultant displacement of the wave, or we can say it is the resultant wave. This equation represents the resultant wave whose amplitude is a, which is given by this equation, and whose phase angle is theta. So we have amplitude, we have the resultant wave, and this is the phase angle. Now we know that the intensity of wave is actually proportional to the amplitude square. So intensity of any wave is directly proportional to the square of the amplitude. That means it should be proportional to this value, or it is given as I is equal to some constant a square. So we get the value I as k a1 square plus k a2 square plus k to a1 a2 cos phi. This is the required value of intensity. Now we have to maximize it for constructive interference and minimize it for destructive interference. In both cases this situation is same. This relation will remain same whether it is the case of constructive or destructive. The answers for amplitude square, wave equation and intensity will remain same. So first here, now this is still constructive के बारे में ही हम अभी बात कर रहे हैं. I can be written as k a1 square plus k a2 square plus 2 root k a1 under root k a1 cos phi into root k a2. Okay, so this term is 2 root k a1 root k a2 and into my cos phi. This is the equation of intensity. Now to maximize the intensity or to get constructive interference, the value of this cos phi should be maximum, and the value is 1. Okay, the maximum value of cos phi is 1, which we get at the angles when phi is equal to 0, 2 pi, 4 pi and so on. So for constructive interference, cos phi should be 1, which implies phi should be 0, 2 pi, 4 pi and so on. So these are the required conditions for constructive interference. This phi is the phase difference, and we know that this phase difference phi is equal to 2 pi by lambda into path difference. Let this path difference be p. Here p is the path difference. So we can substitute this value here. According to that, 2 pi by lambda into p will be either 0, 2 pi, 4 pi and so on. That means the path difference should be 0. If we solve this, then we get p is equal to lambda. So 0, lambda, 2 lambda, 3 lambda and so on. Or in general we can write it as n lambda, where n is equal to 0, 1, 2 and so on. So this is the condition for constructive interference. This is the condition for constructive interference. For constructive interference, cos phi should be 1, phi should be 0, 2 pi, 4 pi and so on, and path difference should be equal to integral multiple of lambda. Now for destructive interference, right, for destructive interference, cos phi should be minimum, that means minus 1. Cos phi should be minimum, that is minus 1. If it is minus 1, phi should be pi, 3 pi, 5 pi and so on. So in that case the phase difference should be odd integral multiple of pi, 3 pi, 5 pi and so on. And if phi is this, then path difference, in terms of path difference, it can be written as 2 pi by lambda into p should be pi, 3 pi, 5 pi and so on. So path difference should be, if we solve this, we get path difference should be lambda upon 2, 3 lambda upon 2, 5 lambda upon 2 and so on. Or in general we can write it as 2n minus 1 lambda by 2. Path difference should be 2n minus 1 lambda by 2 in case of destructive interference or dark fringes. That means the resultant intensity at a point is minimum when the phase difference between the two superposing waves is an odd multiple of pi. Phase difference should be an odd multiple of pi, or path difference should be an odd multiple of lambda by 2. This is an odd multiple of lambda by 2. Then the condition is destructive. While for constructive, the phase difference should be even multiple of pi, The phase difference should be an even multiple of pi, and path difference should be an integral multiple of wavelength, that is n lambda. So these are the conditions for constructive and destructive interference that we get during Young's double slit experiment. In next part of this video, we will continue to find the width of these fringes, these bright and dark fringes that we get in Young's double slit experiment. So stay tuned for the second part of this video.